Hello. So this very short video is to show you how to sample from a categorical distribution using what's known as the inverse CDF method. There are other methods, but this is the simplest one. So here I have a categorical distribution. I show you the probability mass function, and I am pretending I only have 3 outcomes, but this generalizes to however many outcomes you have. And in this example, the probability masses of the outcomes are 0.2, 0.3, and 0.5. All right? Now, when I know the PMF of a distribution, I can figure out the cumulative distribution function. So I show you here for the same outcomes, 1, 2, and 3, 1, 2, 3, the cumulative probability. So the cumulative probability works like this. So we start at 0, and it stays 0 until we hit the first outcome, when the function suddenly jumps to 0.2, which is the probability of the first outcome. So you see that this height is the probability of the first outcome, this number here. The cumulative probability then stays at 0.2 until you hit the second outcome, at which point the probability jumps by 0.3. Which gives us 0.5, 0.2 plus 0.3. Then the cumulative probability stays at that until we hit the third outcome, at which point the cumulative probability jumps by a total amount of 0.5, because that is the probability mass of the third outcome. As we already had accumulated 0.5, when we add 0.5, we make 1. Now, of course, in a discrete space, there is nothing really in between these outcomes. So there are no outcomes other than 1, 2, and 3. So I'm showing you that there are discontinuous jumps, right? And why are these jumps discontinuous? Because our space is discrete. And by definition, or by convention, the cumulative probability in between two outcomes is considered to stay flat, even though, of course, in a discrete set there is nothing really in between. Okay, now the inverse CDF method works as follows. We figure out the cumulative distribution function, is this plot, and we sample by working out the inverse. So imagine that you get a uniform number distributed between 0 and 1. Now that number would fall in this interval here. All right, so let me show you the interval. I don't need the ruler, I don't know why it showed up. There you go. A uniform number generated between 0 and 1 would fall in this interval. We would then map from here to the inverse of the CDF. So essentially, if you got, for example, I don't know, 0.75 or something close to 0.75 here, you would just work out where it intersects, where a horizontal line parallel to the x-axis intersects the CDF. And you would see that by definition we agree that in this discontinuous jump we are mapping to outcome 3. Okay, so this would give you, through the inverse CDF, you would map 0.75 to outcome 3. Now from my drawing, I hope you can see that 50% of the samples, 50% of the points along this long line will all be mapped to outcome 3. Whereas if you were to get, say, I don't know, 0.27, then the inverse CDF would map this to outcome 2. And this will happen for 30% of the points that are distributed along this line. And finally, if you were to get something like 0.05, an inverse CDF method will map it to outcome 1. And you can see that this will happen to 20% of the points that distribute along this line. That's why we draw a uniform number along this line, because the inverse CDF will map the correct proportion of such points to the outcome whose probability mass corresponds to that proportion. Okay, so if I give you now, let's make a quick example, 0.33, 0.47, and 0.88. Let's see which samples I get. 0.33 is somewhere along this space, right? So this will give me outcome 2. 0.47 is also somewhere here. So this will give me also something like outcome 2. And 0.88 is somewhere here. So this will give me an outcome 3. This is outcome 3. I hope this helps.